going to do an example that's a real integral, right? Limit dx over x squared plus 1 from negative infinity to infinity, which equals the limit. And I'm going to show you how to do this using complex numbers, and this actually makes things really pretty easy. So I'm going to do it in the complex plane, and the reality is I want to integrate over this entire thing. But that's a little difficult to do. So what I'm going to do instead is I'm going to chop it off at negative r and r, and then I'm going to let the limit go to infinity. So this is what I want to integrate if this is the complex plane. So here we have the complex plane. But I'm going to use everything that Cauchy did to help us out. So on top of what I actually want to integrate here in the red, I'm going to throw on a semicircle. Like so. And so Cauchy has made it really easy to integrate around this. And I'm going to show that we can integrate the green pretty easily, and then we can get the result in red that I want by just doing the integral of the entire closed loop minus the integral of the green. So here's the basic setup. What I want, and let's not even do this. The integral from negative r to r for any real number r of dx over x squared plus 1 equals the integral over gamma. Let's call this whole shape be gamma, and just this will be, I don't know, how about delta, like so. So this integral, just the red part, is going to be equal to the entire integral of dz, since now I have complex numbers. Maybe I should write in black. dz over z squared plus 1 minus the integral over delta, which is just the top half of the semicircle. Right? So the integral along the red is just the integral over the green and the red minus the green is basically what we say. Well, to compute this, let's factor. Let's just do all these integrals in turn, in fact. I'm going to compute these two integrals and I'll have the result. I won't actually compute them. I will compute this one. So z squared plus 1 equals, I can factor dz over z plus I, z minus I. Is this holomorphic? No, because I lives up there. Negative I lives down there, so we don't care about that. But I can rewrite this as the integral over gamma of 1 over z plus I over z minus I dz, where this, the numerator, is holomorphic around inside of gamma. So this, by the Cauchy integral formula, equals 2 pi I times f of I, where f is just the numerator, 2 pi I times 1 over I plus I equals 2 pi I times 1 over 2I. Oh, that just equals pi. So this is equal to pi minus whatever this integral is. So now we just need to compute just the top half of the semicircle, the delta here, which looks a lot like gamma, but it's supposed to be a delta. So I'm going to compute that. The integral over delta of dz over z squared plus 1. Well, I actually don't need to compute that. So what I can do is I can take the integrand. That's going to be less than, if I make the denominator smaller, it makes the whole thing bigger. And z along the semicircle is always r units away from the origin. So this thing is less than or equal to the maximum value of the integrand times the length of the arc, which is just half a circle, which is pi r. So this is equal to pi over r. So I get pi over r for this integral. So this is roughly. And as r goes to infinity, this goes to pi. So the limit of this thing equals pi, and we're done.